recording now.
This meeting is being recorded.
Thank you for telling me that. So, share screen. Hi, Sam.
Hi there. Good to see you.
Oh, Sam, haven't seen you in a coon's age.
Yes, Jim. We'll talk sometime.
Right.
So there's the title. So the Yang Baxter equation and its relation to the 24 cell. This is joint work with Andy and Steve. It's quite old now, but I thought it was sort of interesting after what previous talks have been, and I thought it may be a good idea to resurrect it. It's the 24 cell is a bit of a come on because what happens is, well, you'll see as we go along. So what is the Yang Baxter equation? So I don't know. I can get rid of this here. Does that help? So the Yang Baxter equation, now designated YBE. So I've written it in this form here. S is some function, so it's a kind of cubic equation. We call this a switch if it satisfies this, and I is the unit interval. The product here could be the Cartesian product or the tensor product. So it could be either. The tensor product is harder, but I'm just going to be considering the ordinary Cartesian product today. So what is useful about the Yang Baxter equation? Well, it turns up all over the place. It's one of those fundamental equations which, describes life. It's first used in statistical mechanics, but has applications to algebra, physics, information technology, and knot theory, as well as others. So I'm, of course, interested in knot theory, and it's a sort of analog of the Reidemeister 3 move. So let's so supposing we've got a crossing, see if I can draw this. So there's a positive crossing of a knot diagram, and we imagine that S is this map here. So this is a right-handed twist through 180 degrees. Now, if I do this switch down here, say, and then I do a unit, doing anything, and now I do the switch here, and do nothing here, and now I do the switch again here, like this. Okay, so this is, if you like, S cross the interval composed with the interval cross S composed with S cross the interval. Then, and I do it the other way around. So if I do a twist here and nothing here, and then I do the twist here, nothing here, and now I do the twist here, then you'll see that, so this is I cross S, S cross I cross S. And you see you can deform this arc here to this position here, so these are essentially the same. And that's Reidemeister 3 move. And so that's why it's of interest to me. I could say that the middle stage going from here to here is a sort of triple point. So let's do black for that. Let's change color. And so, and then I've got this one. And then let's do, say, blue. So that's the midway stage, and one of these is the top. Let's and we've done down the bottom. So this is top, and this is middle, and this is bottom. So these things have to be stratified like that in order for this to work. So anyway, that's why I'm interested in the Yang Baxter equation. And now what is the 24 cell? Right, well, so here's a joke to try at a mathematical party, assuming you go to such things. You've got a sequence. It goes 1, infinity, 5, 6, 3. Now, how do you continue? All right. Does anybody know the answer? Well, it's the number of regular polytopes or faceted solids in increasing order of dimension. So there's only one in one dimension. There's an infinite number of polygons, all regular. There's the 5 platonic solids, of which I have some here. This is a cube. You can see it. It's starting to become a Sierpinski cube, which is here, if you can see it. It hasn't got there yet, and never will. So hang on, there's some people wanting to come in. So I'll let them in, admit all. They're joining. Okay, so sorry for that interruption. And then there, of course, there's the, I don't know if you can see it, that's the icosahedron. And the dodecahedron in the form of a puzzle, which I have never tried to attempt, because I know I'll never get it back to this stage ever. It's like Rubik's Cube, only this is Rubik's dodecahedron. And something else which isn't regular. Now, I don't know if you can see this. This has got one vertex which has got 3 edges coming out of it, and other and another somewhere. Or maybe they all have 3. Anyway, it's not regular. It's called a rhombic dodecahedron, and it will make its appearance soon. Okay. Right, so here's a few models. So this is what I just said. And then when we go to 4 dimensions, there's 6 of them. Now, they the first 3 I mentioned, which are the tetrahedron, octahedron, and cube, they have a formulaic definition. So the tetrahedron is the cone on a triangle, which is itself a cone. So we could write it as C3 B0, B0 being a pair of points. No, sorry, B0 being a point, sorry. The octahedron is the repeated double cone or suspension of 2 points, S0. And the cube is the repeated Cartesian product of the unit interval, so I cubed. So those 3 have a sort of universal definition. So you could go up in any dimension, you see. So the answer to this is it goes 3, 3, 3, 3, 3 forever. and but there aren't any more. But there are analogues in 4 dimensions of 3 of the well-known solids. So we've got the icosahedron and the dodecahedron have big sisters in dimension 4. So one is the 120 cell and its dual to the 600 cell. So they're quite complicated. There is one more 4-dimensional regular solid, the 24 cell, which has no regular relatives. Although, rather like the cube and the octahedron and the tetrahedron, it does have a method of repeating itself in all dimensions, but it's only in 4 dimensions where it's regular. In other words, it's the same everywhere. And in 3 dimensions, it is this rhombic dodecahedron. And I will describe how that is defined. So how do I define the 24 cell? So you take a 4 cube, so a cube in 4 dimensions, and on each 3 cube face, you attach a cone with base this face. And if you do it correctly, you get this 24 cell, you see. To do it correctly, you do the following. You take a 4 cube, you take its center, and from the center, you can then cut up the 4 cube. See, the 4 cube has 8 sides, 8 cubic sides, and you take a cone on the center and cut it that way. Then you take another 4 cube of the same size and stick on these pyramids, okay? And you get the 24 cell. So there are 8 cubic faces and the resulting apexes. Together with the 16 vertices of the original 4 cube, this makes 24 vertices of the 24 cell. So 16 plus 8 is 24. So what's next?
Roger, can I ask about this construction?
Yeah, sure.
So what you're saying, you just invert these pyramids. You basically just cut them from the cube and you put them on the outside of the
if you
cube
like,
instead of on the
you
inside.
reflect this.
Yeah, right.
You reflect it in a face.
Yeah, right.
Okay, so the origin under each reflection goes to another vertex.
Right. Yes, thank you.
And I don't know if you can see this, but when you do this construction in 3 dimensions, you lose an edge. Now you see, I've inked in the edge you lose. You get a rhombus here, which is flat, but it is part of the edge of the original cube. So anyway, it's good fun to think about that. Right. Now the Hurwitz ring H is the subring of the quaternions with coefficients in Z with a half added. Okay. L is just the Lipschitz subring where you just have integer coefficients. Now you might think, because we all know about the Gauss integers in the plane, and so you would imagine that L would be the logical generalization of the Gaussian integers, but you need the Hurwitz ring, which is bigger, because the Hurwitz ring has a sort of Euclidean algorithm. which the Lipschitz ring doesn't have. So that's why it's a better ring. Okay. So what are the units of H? So these are the invertible quaternions. They've all got unit length. And there are 24 of them. And plus or minus 1, plus or minus I, and so on, plus or minus j, plus or minus k. And then a half, because we were allowed to use a half, plus or minus 1, plus or minus I, plus or minus j, plus or minus k. There are 16 of these. There are 8 of these. And so that gives us the 24 vertices. And because they're units of a ring, they actually form a group. And I am grateful to Martin and Andy for telling me what this group is. It's the binary tetrahedral group, or tetrahedral group of symmetries of the tetrahedron, and then it's binary, so it's sort of multiplied by 2. Or another way of looking at it is SO23, and we'll come back to that later on. So it's a special, sorry, not SO23, I mean SL23. Sorry. I don't know why I put an O there. So that's a misprint. What's happened to my, so that should be L. So it's 2 by 2 matrices with entries in the integers mod 3. So we've got the orders. 1 has order 0, minus 1 has order 2, and these guys, plus or minus I, plus or minus j, plus or minus k, have order 4. If you've got a minus 1 here, you get it's order 3. If you've got a plus 1 here, it's order 6. And it's very interesting to see why that is so, because multiplying quaternions is the bane of my life. But if you write, say, 1 plus, let's say minus 1 plus u, and you want to square it, u now is going to be this part here, which is the spatial part of the quaternion. So if I multiply that by minus 1 plus u, I get 1 minus 2u plus u squared, but u squared is 1 because it's u squared is the same as u dot u, and u dot u is 1. Okay, so this is 2 into 1 minus u, but I should have put in a half here, you see, so that would be a quarter, so it's over 2, so this is over 2, and so this is 1 minus u, and you can see how it's going. I've changed minus 1 plus u into 1 minus u, which is the negative of this, so you can see how it's going to be of order 3, and in fact with 1 there you get order 6. So that was a little digression onto multiplying quaternions. So what have we got next? Oh, here we are. Now, if we take all the, it's a bit, I can make that a bit smaller. Okay, so this is the 4 cube, and the vertices are these 16 Hurwitz units. Okay, so, and I've put all the ones which have got a plus 1 in, they're all joined up by red edges. okay? And all the ones with -1 are joined up with blue edges. So these are two cubic faces, the red face and the blue face, and they're joined by black arcs, okay, which are there, okay? And that's how they appear in that that description, okay? So that's a 4 cube. And the other thing of note is that the other ones, oh, I see. So finding the new vertices, how do I get the new vertices? I've got a cube, take a face of the cube, say, and in this case, just for example, I've said take the one with the vertices plus or minus a half, plus I over 2, plus or minus j over 2, plus or minus k over 2. And the center of this 3 cube is I over 2, right? And if I reflect in naught in I over 2, I get I. So remember the construction of the 24 cell is that I stick on the cone onto the boundary. Okay, so, and then the cone point is I. Okay, so, and that construction gives the extra 8 vertices, and these form the vertices of a 4 octahedron, which I think there's a picture coming up. Here it is. So that is a bit big. So the plus or minus I, plus or minus j, plus or minus k, plus or minus 1, they all form the vertices of this 4-dimensional version of the octahedron here. So, and then we put them both together to get the 24 cell. I think we can make this a bit bigger. So you need to stare at it a bit to see what's going on. This is the red cube, which I talked about earlier, and this is the blue cube. And I've taken the one cone point here, which is 1, referring back to it. So, and I've coned it with black edges onto the red cube. Okay, so this is one of the cones, and then that's repeated all the way around, which I've done in green. So that is how the 24 cell is made. So you're probably sitting there saying, what's this got to do with the Yang Baxter equation? And quite rightly. Well, this is what happens. If we're trying to find a solution to an equation, we usually start off with a linear version and see how we get on, and then make it, and then when we've got a linear solution, maybe try a quadratic solution and so on. So let's start off with a linear solution. And A and B are elements in some associative ring. And we assume A and B are invertible because that makes life a lot easier. And look at this equation here, which is, you've got a commutator here equal to another commutator here. And there are various ways of writing it. And this, in fact, is a sort of group theory type commutator. This one here, you see A inverse B inverse AB, and this is just the ordinary additional. Anyway, so these are various ways of writing this equation, which I call the fundamental equation. And a pair AB is called a fundamental pair if they are a solution of the fundamental equation. And for good measure, we assume that A minus 1, and B are invertible. So the original solution was if A and B is a fundamental pair, and C is defined in terms of A and B by this formula, and D is this formula, 1 minus this this group type commutator, then S A, B, C, D is a solution to the Yang Baxter equation, which we called a switch. Okay, so so that's not too difficult to prove. And why does it work? Well, you multiply things out, you look at the 7 equations, which you get by looking at opposite sides, and you get 7 equations, which I've written out here. And this is just this commutator xy minus yx. And then you do some algebraic manipulation and Bob's your uncle. So that's how that works. Now, we still haven't got to the 24 cell.
Roger, where does the interval come into play?
The interval, sorry, which interval?
In the Yang Baxter equation.
Oh, well, I'm saying that, well, what you get is, sorry, let me see, you got, so it would be 1, so A, B, C, D, I guess, 0, 0, 0, 0, times A, B, C, D, 0, 0, 1, 0, 0, and so on.
Thank you.
Yeah, can you do the rest? And then,
Yeah.
okay, so you get 7 equations, and they are this, right? And then you do manipulation. So, right. So let's suppose things commute, and it's a lot simpler. And these are 2 possible solutions. Where in this case, this is an example where D is invertible, and this one is A is invertible. But if A is invertible, then D is 0. And anyway, in terms of B and C, so we call this the generalized Alexander switch. So a special case of this, when B equals 1, is called the Burau switch. So if you put B equals 1, you get the Burau matrix. And you can put BC equals 1, and of course then that becomes 0, and you get B here and B inverse here. And that's been considered by Manturov when he was finding some invariance of virtual knots. So that's a commuting case. Now, what about the non-commuting case? Well, so we've got this. So we've got these equations, and they have to satisfy these horrible equalities. And here's an example. There's the Budapest pair, which gives me that solution. Now, how do I come up with that? Well, and why is it called the Budapest pair, or the Budapest solution? I was in Budapest visiting Richard Riemanni, and he'd gone off to do something, and I was stuck in a B&B on the outskirts of Budapest. And the interesting thing about this this bed and breakfast is that it was only a small place, but every time we came down for breakfast, there was huge number of beautiful girls who were having breakfast. and they obviously weren't staying there. So I wondered about this. Apparently, they were coming from next door, where there was a gentleman's club, and I don't know what they did there. I just gave them tea or something, I suppose. But anyway, so I had time on my hand, and I just fiddled around by hand and came up with this solution. And when I met Andy, I said, "Can you throw your computer and see what you can find at this?" So, and he came up with various examples. Of course, for the IJs and so on, I mean, you obviously can just rotate I and J and K and so on, and get similar examples. But then you imagine the problem of trying to find solutions which are quaternions. What can you do? You can combinations of 1 and I and J and K. Well, it's a computer. You can't just do anything. So you could try integers, and then if that doesn't work, or if that doesn't give enough solutions, you can try a half or a third or so on. But when you did a half, then these came up. So, for instance, this is a fundamental pair where these are Hurwitz units. Okay, and then I just mentioned here that if you've got a solution, you can stick in a variable t, commuting field variable, and that's useful. But I thought I'd just mention that. Anyway, you can. So Steve and I managed to show that if A and B is a fundamental quaternion pair, then A minus 1 is a unit quaternion and B is at right angles to A. So to say that A minus 1 is a unit quaternion means that A lies on the 3-sphere center 1 and radius 1, right? So you get loads and loads of examples from this, and all you've got to do is make sure that B is at right angles to A. And now, how do you do this? Well, you do a bit of quaternion multiplication. So here's a quaternion A, okay, so it's got a real bit, and then it's got a coefficient of I, coefficient of J, and coefficient of K. And alpha is the temporal part, it's the time part, and A is the spatial part, this little a here. And so any quaternion can be written as a time part and a spatial part. And then you can write down the multiplication. A times B is, so alpha times beta, minus A dot B, so that's the scalar product, and then a kind of linear combination of the A's and the B's, and then the vector product, A cross B. See, so this is all in terms of the sort of things you did at university when you were doing vector calculus. So to prove the above theorem, which is this one here, you substitute in the fundamental equation and do the maths, and you get the answer, which is here, that where is it? Here, it's in other words, the A lies on this sphere and B is at right angles to A. So, so it gives you a whole heap of them, heap of solutions, right? So what I'm saying is that the Hurwitz units being solutions led to more general solutions. But actually, we can do better than that, because we're it's purely mechanical. I mean, you just go through the mathematics and the algebra, and you put one side equal to the other side, and you make conclusions. So it doesn't have to be quaternions. What do you need? You see, you could say, well, you need a field, and you don't want 2 to be 0, so it's a characteristic not equal to 0. Characteristic not equal to 2. And you can write anything in the algebra. This is a different A from that one, as you can see. As A naught, which is something in the field, plus something which isn't in the field, right? And you've got a conjugation. So the conjugate of alpha plus A is alpha minus A. And if A and B are pure, right, then AB is going to be a product, some scalar product, plus some vector product, whatever that means. And this product satisfies the Jacobi identity. You remember, if you've forgotten what that is, it is that A cross B cross C is a plus. Sorry, this is not very good. Plus, so C cross A cross B plus A C B cross C cross A equals 0. I think I've got that right. So that's the Jacobi identity. And for example, the 2 by 2 matrices over some field, which doesn't have characteristic 2. So we can think of a 2 by 2 matrix as a 4 tuple, like this. We're obviously usually write it in the, like this: A12, A21, A22. And then a scalar is identify alpha with alpha 0, 0, alpha. Pure matrices have trace 0. So for example, that. So if you sum that one and that one, you get 0. Conjugation, the conjugate of the matrix is the adjoint matrix, and the norm is the determinant of A. And then there is a scalar product. A dot B is a half the trace of A B bar. So that's an example of something which works just as well, almost, but there is one slight snag, is that the scalar product is not definite. You see, with quaternions, the scalar product is definite. It's positive definite. Well, negative definite if I've written it here, but anyway. So you can have isotropic elements in general. Okay. So what can we say about 2 by 2 matrices? So what are the conditions? Well, you go through the same mathematics, and what you need is the trace of A is equal to the determinant of A, and you don't want that to be 0, and A dot B equals 0. So they're sort of orthogonal in this sense, and we want B to be invertible, so det B is not 0. So these are sufficient conditions for A, B to be a fundamental pair. If the scalar product is definite, so anisotropic, then the condition is also necessary. But that's okay, because we find things like that, and they'll give us solutions to the Yang Baxter equation. So I'm going to do examples here. So now this is the field is the integers mod 3, and we've got 2 by 2 matrices with entries in the field mod 3. So 1 is just the identity matrix, I is 1 minus 1 down the anti-diagonal. J is a sort of Hadamard matrix, and K is also a bit like a Hadamard matrix as well, but it's if you multiply those two matrices together, you should get this one. And then a half of 1 plus I plus J plus K is this matrix here. Half of minus 1 plus I is this matrix here, and so on. All right. So all in all, you get the entries for this the special SL23, the group of 24 entries, which is
So you're giving an explicit identification with
I am, yeah.
Z3 and the binary tetrahedral group.
Yes, exactly. You could try this with the reals, and I put I equal to this, J equal to that, K equals that. But these are what I call the real Pauli matrices because they've got real entries. I think some people also do call these the Pauli matrices, but when you try and do this I plus J plus K, you get this, which is not invertible. So, but it does form a monoid, a sort of.
Those are also called the split quaternions.
Oh, cool. Oh, are they? That I recognize that voice. That's Lou. Is that correct? The split quaternions. Okay. So anyway, but there, lots of examples of solutions which we get from that. And I'm ending the talk fairly early. I bet you'll be pleased about that. So here's some challenges. So if I take these fundamental pair augmented by a variable t to find a Laurent polynomial with coefficients in Z3 of some virtual or welded knot. Let me just say that it's no good looking for something new with classical knots because you don't get anything new with this. But you do get very interesting examples with virtual knots. And it requires a lot of computing and so on to do the maths. So you can try to see what you can find. I suppose I'm challenging here Andy because he's the one who can write the programs. And here's another challenge. Find all solutions of the Yang Baxter equation when, the field is Z5, 2 by 2 matrices of a Z5 or Z7 and so on. So, so that's what I wanted to talk about. Are there any questions? Obviously not.
Well, like Otis P. Driftwood, I missed the entire opera, but I didn't miss it by much. Could you just scroll back through your earlier slides? I'm sorry. I thought we were starting at noon my time.
No, okay. So I'll go right back. So I'll whiz through these things again for everybody's benefit. So
I recognize that.
So to recap everything which is said, so there's the Yang Baxter equation.
Yep.
And has and it could be thought of as the Rheinemeister 3 move. Regular solids, there's 1 in dimension 1, an infinite number in dimension 2, 5 in dimension 3, 6 in dimension 4, 3 for the rest of time.
Right.
Okay, and the 5 regular platonic solids have big sisters in 4 dimensions, but there's one extra one, which is the 24 cell. So it's kind of regular 4 solid. And how do we construct it? Well, you just take cones on the faces of a 4 cube.
Okay.
And we can make these vertices of the 4 cube. They correspond to the Hurwitz ring, the units of the Hurwitz ring. These units form a group, which is the binary tetrahedral group. And they're those. They're the ones which form the vertices of a cube, a 4 cube, and we attach.
Okay.
You got it?
Yeah.
So you attach these guys to cones on the boundary cells to get this.
Right.
And then you want to consider the linear solutions to the Yang Baxter equation. And you come up with this formula here. If you pretend things don't commute, and that's because you've got these 7 equations. And if you're assuming that A and B are invertible, you can do all sorts of things to simplify it, and you get this equation here.
Right. So the binary tetrahedral group is the inner automorphism group of the twofold extension of the tetrahedral quandle. And I'm wondering if your solutions have anything to do with quandle colorings by that extension.
So almost certainly. So I'm not sure what you said, but I'm sure it's true.
So the tetrahedral quandle, which is just 3 cycles, oriented 3 cycles under conjugation.
Okay, so
has a
do you want to write something on the?
Well, I can, but
I can let you share.
Yeah, I'm not on a okay, let's see if I can do this. Okay, that'll be a good enough page then. Just give me a second.
Okay.
Okay, so sorry, that's something completely different. If you look at what am I doing? All are in the way. I've got to get the font large enough here. Okay. Sorry about that. What on earth? Okay. Let's see if this works. Okay, that's almost legible. So if you look at 1, 2, 3, 1, 4, 2, 1, 2, 3, 1, 2, 4, 1, 3, 4, and
Did you want 142 or 124?
no, I want 1, 4, 2.
Okay.
And then 1, 2, 3, 1, 2, 4, 2, 1, 3, 4. What's the other one? 2, 4, 3. So those 4 elements form a quandle under conjugation.
Right.
And it's the same thing as a field with 4 elements. That quandle, the inner automorphism group of that, I don't know why I'm not typing where I want to be. There we go. That inner automorphism group is A4. And the quandle has 2-dimensional homology with Z2 coefficients isomorphic to Z2. So there's an extension of this quandle. And let's call the extension Q bar. And the inner automorphism group of Q bar is, sorry, we're off screen, aren't we? Is the binary, okay, I've lost my cursor here. There we go. That's equal to the binary tetrahedral group.
Okay.
And so I'm wondering whether your solutions to the Yang Baxter equations have something to do with the quandle coloring by this twofold extension. But you tell me that you're not going to get anything interesting unless you're in the virtual case. And I bet there are interesting quandle colorings by this extension.
Well, when I say you don't get anything interesting, all I'm saying is that you could have done it. I mean, what we're defining here, or I didn't say, is a biquandle.
Ah, right, so, right. I see. Okay. Yeah. All right. So, that makes, yeah, right.
So what I'm saying is that you don't get anything which you couldn't do by using a quandle.
Sure.
In the classic case. So maybe that is the answer.
Okay. All right. Yeah. Okay. I missed that. Of course, your equations defined a biquandle structure. Yeah.
Okay. Well, that's interesting. I mean,
do you also have applications of this to surfaces in force space?
Me or Roger?
Am I supposed to answer that?
Well, I meant it to you, but maybe it actually goes to Scott. Yeah.
Not other than the classical CJKLS, the quantal 3 cocycle invariance. Mm-hmm. That particular quandle is nice for the figure 8 knot. And so 2 twist spins of the figure 8 knot probably can be, they're probably Hatakanaka it's probably Hatakanaka got minimal triple point numbers for that. By means of that particular quandle.
I mean, it would be interesting to get to the bottom of that. Relate the two things. Yeah. I mean, since I announced this, I've had all sorts of interesting emails. I mean, got one from Eric, who's also done some stuff similar to this, and he's going to talk about it sometime in the future. Is that correct, Eric?
Yeah, maybe in the not too distant future, maybe in May.
In May, okay. The 24 cell does seem to bring out the weirdness in people. Well, it's kind of unique, isn't it? I mean, it's what was Jack? Do you want to say anything?
Well, I'd like to apologize to the community for talking to anthropologists about this. They asked me about some crazy stuff of Claude Levi-Strauss about kinship systems and myths and things like that. And I tried to answer their questions and wound up in the 24 cell. So there are a couple of papers on the archive about Levi-Strauss by me. And at the beginning, I thought this was a kind of wild goose chase. But as I got into it, I began to take it a little bit more seriously, which I find kind of scary. So
you mean the relationships they were looking at end up diagramming on a 24 cell?
I think you can do that, yeah. I don't know what, I mean, Levi-Strauss has this idea that you take a collection of myths and you look into them and you find that they're little kind of twists, kind of, O. Henry kind of twists, where the system of myths goes off in some direction that you didn't expect. And it's called a double twist. It has a literature. And it kind of looks like a braiding or something like that on some classes of myths. Anthropologists take this very seriously, or used to. I don't know if they do anymore. Anyway, I did my best to say something about it, and now I'm finding myself having to defend it. Anyway, read it. I mean, if you're interested, it's on the archive. And I wouldn't believe everything it says, but there's some interesting examples.
Thanks.
So, very interesting.
Roger, can you put back the fundamental relation from your slides, please? I had a question about that.
I can do that.
It's a question. I mean, this reminded me of something, and I searched and I quickly found it's also in your paper with Turaev called While Algebras and Knots.
Oh yeah.
And there it seems that that you did the same fundamental relation. Well, it was written slightly differently, and then you specialized a little more, and you got some solutions in the Weil algebra with finite coefficients or something like that. Is that right?
That's correct. Yeah.
So how is this related to what you're doing now? Are these quaternion modules quotients of those modules or not?
Well, what we looked at, we suppose that S had order 2, so that S squared is the identity. And then the fundamental equation gets a lot more simplified, and you get solutions which are in the Heisenberg ring. There's a lot of stuff here.
So what's the order if you take these quaternion solutions, or these matrix solutions you just showed us?
Well, of course, they won't be quaternions. I think I mean, you've got me on the spot now because I'm trying to remember what was in that paper.
No. What you just said is that S squared equals 1. That refers to the current work or to the old paper?
No. This is to the work with Turaev.
So in that work, S squared was 1. So S was an evolution.
S squared was 1, and that made things a lot simpler. Yeah.
Right.
But yeah.
So here for this, what you just presented, does S have finite order, or
No.
And if so,
Well,
no?
I guess it will have finite order if the coefficients are in the Hurwitz, Hurwitz units, because obviously there's only a finite number of them. But I think in general it won't have finite order.
So so this is not a special case of that. It's just the same relation but different solution.
Yeah, sure. Yeah.
Right. And by the way, the formula right underneath that, I think this is wrong. The commutator, because it should be a commutator of B with A inverse BA, not B inverse AB with A.
Sorry, the commutator with. I might well have made a typo here. What did you say?
Yeah, the right hand side. I think it's B with A inverse BA.
Oh, okay. So
which
I've
would be
got
consistent with the one underneath.
Yeah. Okay. Yeah, you're probably right.
Yeah.
I mean, I have been known to make mistakes.
Mistakes follow humans.
Yeah.
Thank you.
Okay. Are there any other questions?
So presumably you get a representation of the braid groups from this.
Oh yes, you do. Yeah, yeah.
Do you know what the images of those representations are? Are they finite groups or infinite?
What I can tell you is that you don't seem to get. I mean, if you take the braid, which is trivial under the Borel representation, it's also trivial under this, so you don't unfortunately manage to get anything better than Borel. On the other hand, for extended braids, like virtual braids or welded braids, then you certainly do get a lot of nice information from this.
Okay, thanks. There's some references where I can read about this.
Yes, I think in the paper with Budden, it explains why this is so, which I can send you a copy if you remind me.
That'd be great.
When Roger, when you make your notes with a couple of corrections, you could drop a little list of references at the bottom of the notes.
I will do that. Yeah, I should have done that anyway. Yeah, quite agree. Well, okay. Now we're going to have an Easter break now for 2 weeks, and then we'll come back with possibly Sam giving a talk. Would it be too soon for you, Eric? If you're there.
I'm here. Let me look at my count. I think the earliest I could do would be like the second Tuesday in May.
Second Tuesday in May. Okay, that's the date.
The 10th.
The 10th of May. Okay. Thanks, Eric. Yeah, I look forward to that.
Yeah, great. Thank you.
Okay, so I'll stop sharing now and call it a day, and I'll see you in 2 weeks' time.
Great.
Thank you, Raj.
Please send the notes to me. I'll put them up put them in the Dropbox.
Yeah.
Thank you very much.
Thank you.